Hi everyone. Now we are at eigenvalues and eigenvectors, lecture number 11. So in this lecture number 11, we are going to discuss one theorem. It is Cayley-Hamilton theorem, very powerful theorem. Only theorem statement I will discuss. Proof is not required. So the theorem statement is this. So every square matrix satisfies its own characteristic equation. So roughly I will explain what is meant by that. Okay. See, let first let A be an n by n matrix. Okay, an n by n matrix. N by n means it is a square matrix. Okay, n rows and n columns. Then its characteristic equation is then its characteristic equation is determinant of A minus lambda I is equal to 0. Equal to 0, that's why it is characteristic equation. If it is just only determinant A minus lambda I, it is called characteristic polynomial. Okay. Now I want characteristic equation according to theorem statement. So what is the general form of the characteristic equation? So that is, just I'm explaining roughly, it is not the proof. What will happen behind the screen I am telling. So what is general form? Some constant into lambda raised n, because A is of order n by n, therefore nth degree characteristic equation I will get. Okay, A naught lambda power n plus some constant a1 into lambda raised n minus 1. Okay, plus up to so on. The last one is some an. This is equivalent to 0. This is characteristic equation, general form of the characteristic equation. Okay, see, for example, that is right here. See, x square minus 2x plus 1 equal to 0. Take a second degree equation. Substitute x is equal to 1. For example, let x is equal to 1. Substitute back, what happens? Substitute here. Then what will get? X is 1. So 1 minus 2 plus 1 equal to 0. Then 0 equal to 0 we are getting. Therefore, I can say that x is equal to 1 satisfies x square minus 2x plus 1 equal to 0. I can write this statement, right? X is equal to 1 satisfies x square minus 2x plus 1. Satisfies means what? There is a root for this equation. LHS equal to RHS you will get. Same thing. Look at here statement. Every square matrix satisfies its own characteristic equation. This is a characteristic equation. The matrix A satisfies this characteristic equation means what? Instead of lambda, you substitute matrix A, and that should be equivalent to 0. Look at here. I can say that x equal 1 satisfies this equation means substitute back 1 instead of x. Then you should get LHS is equal to RHS. Same story here. Okay. Now, so this implies, yeah, so A naught, instead of lambda I am substituting the matrix A, so A raised n plus A1, A raised n minus 1, okay, plus up to so on, plus an equal to 0. But this equation is not make sense. Why? Because A naught is a number, A is a matrix. So A to the power of n, again a matrix. So number into matrix is, this is a matrix. Similarly, this is also a matrix. Matrix plus matrix is again matrix. Up to so on, plus an. An is a number. So matrix plus number is not make sense, right? See, for example, let us take 2 by 2 matrix 1 2 0 1, for example. 2 by 2 matrix I'm taking, plus some number 5. Does it make sense? This does not make sense, right? Matrix plus matrix, then only that is makes sense. It does not make sense, right? It is not meaningful. That's what I'm telling here. So this is a matrix plus it is a matrix plus up to so on. It should be matrix, but it is a number. So therefore, it should be a matrix. So how it should become make sense? Then instead of an, you write as identity matrix. identity matrix of order n. Now this is makes sense. It is not 0. Now this is 0 matrix, null matrix it is. Now this is makes sense. Why I am writing I to make it make sense, and this will be very clear if you go through the proof of this theorem statement, but proof is not required. Just so this is about Cayley-Hamilton theorem, right? So depending on this, let us do some problems. Problem number 1. So look at 3 by 3 matrix is given to us. Then verify Cayley-Hamilton theorem. First question. Cayley-Hamilton theorem means every square matrix satisfies its own characteristic equation. So already square matrix is given to us. We want characteristic equation. Okay. Then find out characteristic equation first. So first one is characteristic equation. After that we will verify. Okay. Characteristic equation. So therefore a minus lambda I equal to 0. So now let us substitute back what is a. So determinant of, first take the matrix A. What is matrix A? 1 0 2 1 0 2 and minus 1 1 1 and 0 1 2. Okay, this is matrix A minus lambda into identity matrix of order 3 by 3. So 1 0 0 0 1 0 and 0 0 1. Okay, and determinant equal to 0. This characteristic equation. Okay, now simplify this. So 1 minus lambda, next minus 1, next 0 and 0 1 minus lambda, and this is 1 and 2 1 2 minus lambda. Determinant, this is equal to 0. Then simplify. See, I told you two methods for finding determinant. One is by applying this operation, right? C1 is modifying as some C1 plus C2 plus C3, and the second one direct expansion. But this method cannot work out here. Why? Because first you write what is C1 plus C2 plus C3 and place C1. You will get this entry as minus lambda, right? Minus lambda. But what about this entry 2 minus lambda? This one 5 minus lambda. But what I want, this column should having a unique element, unique entry. Then that element I will take common. That's what I have done in the last class, right? But here you are not getting unique element in this column. So therefore that method cannot work out. See, if adding these three entries, this entry A11 plus A12 plus A13, for example 2 minus lambda I am getting. Here also 2 minus lambda I should get. Here also 2 minus lambda I should get. Then 2 minus lambda I will take common. But here you are not getting like that. So that method cannot work out. Then go to the direct expansion. Okay. So directly the determinant of this. So first expand through the first entry 1 minus lambda. So 1 minus lambda into 2 minus lambda. Okay. Minus 1. Okay. Next minus of minus plus 1 into 0 into 2 minus lambda is 0. Next 2 minus, so minus 2 is equal to 0 because last one is 0, 0 into something is 0, something which is finite. Okay, then expand it. So 1 minus lambda. Okay, and here multiply this 2 minus lambda, multiplying with 1 first, next minus lambda minus 2 lambda plus lambda raised 2. Okay, and minus 1, close, and this is minus 2 is equal to 0. Next simplify the inner terms 1 minus lambda, and here first square terms, so lambda power 2 minus thrice lambda and plus 1 is and minus 2 is equal to 0. Again expand through 1 minus lambda, so lambda raised to minus 3 lambda plus 1, next through minus lambda, so minus lambda raised 3 and plus 3 times lambda raised 2 and minus lambda, okay, and minus 2 is equal to 0. So first lambda raised 3 minus lambda raised 3 and 3 lambda square plus lambda square plus 4 times lambda raised 2, okay, and what else, minus 3 lambda minus lambda, isn't it, minus 4 lambda, okay, next constant terms, right, 2 minus 1 minus 1, multiply with minus, so we get lambda raised 3 minus 4 times lambda raised 2 plus 4 times lambda and plus 1 equal to 0. So this is a characteristic equation. Now the first question, verify Cayley-Hamilton theorem. So does this matrix satisfies this equation or not? That's what. So therefore by Cayley-Hamilton theorem, write in next page. So by Cayley-Hamilton theorem, characteristic equation. Okay, its own characteristic equation, right? So based on this, therefore, so assume the previous one is, assume this is number 1, this equation is number 1, okay. So therefore 1 implies here, so equation number 1 implies lambda raised 3 minus 4 times lambda raised 2 plus 4 times lambda plus 1 equal to 0. Is it? Check once. Yeah, absolutely. So yeah, so according to theorem, what we want, a raised 3, right, instead of lambda we are putting back a, minus 4 a raised 2 plus 4 times a plus here what I need to write, this is 1 is like an into I, right? So 1 into identity matrix, 1 into identity matrix. Now this is null matrix. So this is by using Cayley-Hamilton theorem. So it has to be satisfied. It has to be satisfied. Then only Cayley-Hamilton theorem is satisfied. So we have to verify this. We have to verify this. Verify this means what? You substitute back all the unknowns. Here unknowns is a cube is unknown. Already matrix A is given to us. So we need to compute what is a cube and we need to compute what is a square. A already given. Identity matrix we know. And simplify these 4 terms, should get null matrix. Then only the matrix A satisfies its characteristic equation. Then it is verified. So we have to do that, right? We have to verify this. So before that, let us compute the unknowns here. Okay, the unknowns are, first a cube I want. So what is A first? The matrix A is 0, 1, 2. So this is matrix A is given to us. Then what do you want? A cube we want, right? So this is given to us. Then we want a cube. So before that I want a square. So a into a first. A square, which is nothing but a into a into a. Okay, this is nothing but, let us do the multiplication. So 1 minus 1 0, 0 1 1, 2 1 2, okay, into multiplication into again same matrix, right? So 1 minus 1 0 and 0 1 1 and 2 1 2, okay. Then multiply, what will you get? So first 1 ones are 1 1, next 0 plus 0, right? Look at here, minus 1 into 0 0, next 0 into 2 0. So 1 plus 0 plus 0, first entry, right? And this entry and this row with second column. 1 into minus 1, minus 1. Next, minus 1 into 1, minus 1. Next, 0 into 1, 0. Plus 0. Over. Look at first row with second column. Okay. Next one. First row with third column. 0. Next, minus 1. Next, 0. Plus 0. Over. Next, similarly, second row with three columns. First, second row with first column, 0 plus 3, 5. Okay. Next one, we want a cube. So a square into a I want, right? So a square into a. So which is a cube. So let me write first a cube. So a cube is equal to a square into a. Okay. So now what is a square? Just now we computed. So 1 minus 2 minus 1 and 2, 2, 3. Similarly 6, 1, 5. 6, 1, 5. Okay. And into a square. Into a. What is a? So 1, 0, 2. 1, 0, 2. Minus 1, 1, 1. Next 0, 1, 2. 0, 1, 2. 0, 1, 2. Right? Then multiply this. So what will you get? Yeah. Yeah, see. 1 1 is 1 plus 0 minus 2. So minus 1. Directly I'm writing. Okay. Next, first row with second column. Minus 1, minus 2, minus 3, minus 1, minus 4. Okay. Next, 0, minus 2, minus 2, minus 4. Okay. Next, 2, 0, 1, 1 1 is 1, 5 to 10, 11. Okay. So this is about a cube. Okay. So now all the unknowns we obtained, then substitute back here. Okay. So what is given to us here? This is a characteristic equation, and here we need to substitute back. So we need to compute what is this value, LHS value, right? A cube minus 4a square plus 4a plus I. So this one we have to compute. So let me write that a cube minus 4a square. So a cube minus 4 times a square, right, plus 4a square, 4a, and I want plus I. This one I want, what is this value? It should be actually null matrix I should get. Let us substitute, let us find out whether it is 0 or null matrix or not. 1 2 1 2 2 1 2. Okay. And next plus I need to write. Plus 1 into I is I only. Now what is I? 3 by 3 matrix I will write. 1 0 0 and 0 1 0 and 0 0 1. Okay. All the matrices we substituted back and simplify. You should get null matrix, then only it is verified, otherwise it is not verified. Yeah, let's simplify. So minus 1 minus 4, how much? Minus 5. Okay, minus 5 plus 4, minus 1, minus 1 plus 1, 0. Okay, I'm adding all. Next, look at this entry, minus 4 plus 8, minus 4 into minus 2 plus 8, right? Minus 4 into 4 to the 8 plus 8. So minus 4 plus 8 plus 4 plus 4 minus 4, 0, and plus 0, 0. Look at next, look at this entry, minus 4 plus 4, 0, plus 4 into 0, 0, 0 plus 0, 0, 0 plus 0, again 0. Next, 8, minus 4 into 2, minus 8. So 8 minus 8, 0, 0 plus 4 into 0, 0, 0 plus 0, 0, plus 0, 0. This entry is 0. Next, look at this one, 3 minus 8 minus 5 minus 5 plus 4 minus 1 plus 1, 0. Similarly, all these things will get 0. Check once. Look at, indirectly it is verified, therefore verified. Our first question is verified, that's it. Look at the first question. What is the first question? Verify Cayley-Hamilton theorem, right? First one. Look at here, verify Cayley-Hamilton theorem. Verify Cayley-Hamilton theorem. Therefore, Cayley-Hamilton theorem is verified. The square matrix A satisfied its own characteristic equation, that is the matrix A satisfied its characteristic equation. Okay, characteristic equation. Okay, over. Next, second one. What's second question? Come back. The second question is find a cube and a power 4 by using Cayley-Hamilton theorem only. For example, see, look at here. A is already given to us. How to find a cube? Just now I computed already. A cube. A into a square I will get. After that, one more time multiply with a so that a cube will get. But such kind of calculations I don't want. What I want, by using Cayley-Hamilton theorem only, I have to compute both a power 3 and a power 4. How to find those? Let us look at. So by Cayley-Hamilton theorem, you have to calculate, right? A cube and a power 4, a power 3 and a power 4. These two things we want by Cayley-Hamilton theorem. So what we got here is, so from here we verified that a raised 3 minus 4 times a raised 2, okay, listen carefully, plus 4 times a, okay, plus identity matrix is equal to 0. This not 0, null matrix, and this one we verified just now, and from this equation only I am going to find what is a cube and a power 4. So look at this one, assume it is equation number, let's say some number 2, already 1 is assumed. So from here let us take, so 1 implies, from here a cube you keep left hand side only, remaining terms you bring to right hand side. So 4 times a square, okay, minus 4 times a minus I, that's it. Now what is 4 times a square? So this is 4 times a square, right? Substitute back. So 4, now what is a square value? This is a square value, right? 1 minus 2 minus 1. So 1 minus 2 minus 1, isn't it? Next one 2 2 3, 2 2 3. Next one 6 1 5, 6 1 5. Okay, this is a square. So 4a square minus 4 times a I want. What is a? So a is, so this is a matrix A, right? 1 minus 1 0, 1 minus 1 0. Next 0 1 1, 0 1 1. Next 2 1 2, 2 1 2. Okay, next minus identity matrix. So 1 0 0 and 0 1 0 and 0 0 1. Okay, and now this will be, what is this? Yeah, simplify and write down. Yes, 4 ones are 4, minus 4 0, and this is minus 1. So first entry is minus 1. Next second entry minus 2, 4 to the 4 minus 2 the minus 8 plus 4 minus 4, so plus 0 minus 4 minus 4. Next third minus 4 0 minus 4 0, so minus 4. Okay, next 4 to the 8 0 0, so 8 only this one. Next 4 to the 8 minus 4, so 4, 4 minus 1, so 3. Okay, next 4 3 is a 12, 12 minus 4 8, so this is 8 and that is 0. Okay, and last row 4 6 is 24 minus 8 16, so this is 16. Next 4 1 is 4 minus 4 0, so and 0, so this is 0. Next, 4 5 is 20 minus 8, 12. 12 minus 1, so 11. So this is a cube. Look at, I have not done a square into a. Only a square and a term only I used. Then I computed what is a power 3. Understood? Look at a power 3 already we computed. This is a power 3 and verify minus 1 minus 4 minus 4 and 8 3 8 and 16 0 11. Same matrix I got here. So this is a way of computing a power 3 higher powers of a by using Cayley-Hamilton theorem. Similarly, a power 4. How to get a power 4? Same equation you take. Okay, same equation. So equation number 2 implies what is that? A cube minus 4 times a raised to plus 4 times a plus identity matrix equal to null matrix. And from this, a cube is equal to 4 times a raised to, right, minus 4 times a minus I. Okay, and I want a power 4, so multiply both sides with a. So multiply both sides with the matrix A. Then what will get? A power 3 into a power 4. And here 4a square minus 4a minus I into a. Multiplying both sides with the matrix A. Okay. Then what will get? A power 4 is equals to 4a cube, okay, minus 4a square minus identity into a is a only. Okay, now substitute back here. What is a cube? Already we computed just now. If it is not there, you have to compute what is a cube, compulsory manual computation. And a square you have to compute, a already given, and simplify, you will get a power 4. Take this one as exercise. Okay, take it exercise. Right, simply compute a cube. Already I computed, only substitution is required. A square also I computed, substitution is required, a already given, and simplify these three things, you will get a power 4. Similarly, a power 5 also I can compute. Again, take this equation, multiply both sides with again a, so that a power 5 you will get 4a power 4 minus 4a power 3 minus a square, like that. Okay, so this is how to find higher powers of a by using Cayley-Hamilton theorem. Right, next question. Last one, find A inverse by using Cayley-Hamilton theorem. A inverse. So far we know how to find A inverse by which method? Gauss-Jordan elimination method, right? And by using A inverse is equal to 1 by determinant of A adjacent of the matrix A. That is second technique. And this is a third technique, finding inverse of a square matrix, particularly non-singular matrix, by using Cayley-Hamilton theorem. Okay, now let us find out A inverse for this. So first, what is given to us is, so next third question here, third question. A inverse we are going to find. A inverse is question mark. Okay, again same equation number 2 implies, so equation number 2 implies, what do we got? A raised 3 minus 4 times a raised 2 plus 4 times a plus identity matrix equal to 0. This is what we verified in the first question. And here keep this I left hand side only, identity matrix. Remaining all these three matrices you send right hand side. So I am keeping in left hand side. Remaining three matrices I am sending right hand side. So what you will get? 4a square minus a cube, isn't it? Minus 4 times a. Simply look at. So now I want A inverse, right? So multiply both sides with A inverse. So then what will get? A inverse into I. So here So either pre-multiply or post-multiply, your wish. I'm doing post-multiplication. So I into A inverse. Okay. I into A inverse is equals to 4 into A square. Or directly you can write, no problem. Just I am telling step by step for a better understanding. A cube minus 4 times A into A inverse. Okay. And which is equivalent to 4A square into A inverse. How much? 4 into A. Next minus A cube into A inverse A square. Next minus 4 into A inverse identity matrix. This is identity matrix into A inverse is A inverse. Look at. So this is A inverse formula. Okay. And there are some non-singular matrix also exist. Before proceeding to this step, we need to verify whether A inverse exists or not. We need to make sure whether this step is make sense or not. This step, what is the step? Multiply both sides with A inverse. If A inverse exists, then only we will multiply both sides with A inverse, right? That we have to make sure before actually. You have to verify. How to verify? So first we have to verify that determinant of A should be not equal to 0. This one you have to verify first. Then only we can proceed this step. This step. If det A is equal to 0, so determinant of A is equal to 0, then directly A inverse does not exist, you can write. Okay. If inverse exists, we can calculate by this technique. Okay. If inverse does not exist, we cannot find. This method cannot work out. Okay. We have to make sure. So what is the determinant of the given matrix? So first, so det A is equal to, so you are getting minus 1. So therefore this is not equal to 0. Fine. We are safe. Right. So det is not equal to 0, therefore inverse exists. Then you can proceed this step, multiply both sides with A inverse. Okay, you have to write here, since, let me write here, since determinant of A is not equal to 0. First you have to make sure this one. Then you have to do this step. Okay, fine. So A inverse is this. Then substitute back all the matrices, 4 into that and all those things. So this is equivalent to 4 times matrix A first. Now what is A? 1, 0, 2. Next minus 1, 1, 1 and 0, 1, 2. 0, 1, 2. This is matrix A minus A square I want. A square. Already we come, that is 1, 0, 0, 0, 1, 0 and 0, 0, 1. Okay. Yeah. So now simplify this. So finally we'll get this one as, let me write here. So finally this is, so A inverse is equals to, so A inverse is equals to, yeah, simplify now. 4 minus 1, how much? 3. 3 minus 4 is minus 1. Next second entry, minus 4 plus 2, minus 2. Next 4 0 is 0, so 1. 1 plus 0, 1. Next similarly 4 0 is 0, minus 2, so this entry is minus 2. Okay, minus 2, minus 2, right? Next 4 1s are 4, minus 2, so 2 minus 4, so minus 2. Make sure that everything is correct. Once again 4 1s are 4, minus 2, 2 minus 4, minus 2. Next 4 1s are 4, minus 3, so 1, 4 minus 3. Next 4 is 8, minus 6, 2, this is 2. Next 4 1s are 4, minus 1, 4 minus 1, so 4 minus 1, 3. This entry, right? 4 1s are 4, minus 1, so 3. Next 4 to the 8, minus 5, 3, 3 minus 4, minus 1. So here 4 into you have to do, am I done? 4 minus 1, 3, 3 minus 4 minus 1, I am verifying once again. Let me verify back. So this is A inverse. Simplify this, I got this matrix. So how to verify this matrix is correct inverse matrix. Just already you got A inverse. Simple given matrix A and you obtain the matrix A inverse, multiply both, you should get identity matrix. Then this is correct. This is a cross verification. Okay. So this is a way of finding inverse of a non-singular matrix by using Cayley-Hamilton theorem. Okay. Next one, problem number 2. Let matrix A 2 by 2 matrix is given, then find this value a power 6 minus 4 times a power 5 plus 8 times a power 4 minus 12a cube plus 14a square value. So before proceeding into this problem, you have to understand how to attack the problem. So A is given to us, don't compute what is a power 6. A power 6 can compute by scientific calcs easily, but I am asking for manual calculations. It will take a lot of time. First a into a square, again a square into a cube, again a cube into a power 4. Likewise, you keep on continuing the calculations, then substitute here and you have to simplify. That is the one way of doing. Use a lengthy one. Just use Cayley-Hamilton theorem. Okay, by Cayley-Hamilton theorem, you can attack this problem easily. How to attack? Look at first by using Cayley-Hamilton theorem. Okay, by Cayley-Hamilton theorem. Cayley and Hamilton both are scientists. Cayley-Hamilton theorem. By Cayley-Hamilton theorem, first we want characteristic equation, right? So determinant of a minus lambda I. First find out this. That implies determinant of 1 minus 1, 2, 3 minus lambda into 2 by 2 identity matrix 1, 0, 0, 1. Okay, this is equal to 0. Now simplify. So 1 minus lambda, just 2 minus 1, 3 minus lambda. Determinant equal to 0. Then find out. So 1 minus lambda into 1 minus lambda into 3 minus lambda and plus 2 equal to 0. 2 by 2 matrix determinant. So 1 3 is a 3 minus lambda minus 3 lambda okay, plus lambda raised to plus 2 equal to 0, which is lambda raised to minus 4 times lambda 3 plus 2 5. How to know that this is right or wrong? Simply, what is the trace? Trace is 4, right? Look at 4. What is the det? 3 1 the 3 plus 2 5. Look at this is the det 5. Like that you can cross verify. Okay. Now this is characteristic equation of the given matrix A. So by Cayley-Hamilton theorem, the square matrix A will satisfy its own characteristic equation. So therefore, by Cayley-Hamilton theorem, Cayley-Hamilton theorem. What I can write? A raised to minus 4 times A plus 5I equal to null matrix. No need to verify here because by theorem, every square matrix compulsory satisfies its own characteristic equation. Okay, so directly you can write like this: a square minus 4a plus 5 into I equal to 0, equal to null matrix. Okay, and now from here we have to play. From this equation we have to play. So look at here, one implies. I want to write first what is a square. So a square is equals to 4a. Listen carefully how I am doing, minus 5 times I. Our goal is to compute what is this value. Okay. So a square is equal to this. I want to generate what is a cube. So multiply both sides with a. Multiply both sides with a. Then you will get a cube is equals to 4a square minus 5a. And now look at a cube I'm getting. So again a power 4 I need to generate. So assume this is number 2. Okay. Now 2 implies multiply both sides with again a. Okay, how I'm struggling to get the required result, you'll get simply I'm generating the required powers a square, so that is this one, a square is this, and after that a cube I'm generating a power 4, a power 5, a power 6, like that. Okay, then multiply with a, you will get a power 4, which is equals to 4 times a raised 3, okay, minus 5 times a raised 2. Okay, assume this is number 3. Next a power 5 times I need to generate, so then write multiply, so 3 implies from 3 want to play with 3, so multiply both sides with again a. What will you get? A power 5, the previous equation I am multiplying. Okay, a power 5 is equals to 4 times a power 4 minus 5 times a power 3, and assume this is number 4. Okay, next one, same one again. 4 implies a power 6 I want to generate, so multiply both sides with again a. What will you get? A power 6 is equals to 4 a power 5 minus 5 a power 4. Yeah, assume this is number 5. So here we will play now. Okay, look at a power 6 minus 4 a power 5 I want to look at a power 6. Already look at right hand side plus 4 a power 5 is there, you bring to the left hand side, so that minus 4 a power 5, that is the required term. Look at minus 4 a power 5. Okay, then so 5 implies, equation number 5 implies, yes, so a power 6 minus 4 a power 5. We need to be very cautious here how we are, what terms we are sending to the left hand side. Only required terms we have to send left hand side, because this is left hand side expression. A power 6, look at the question, a power 6 minus 4 a power 5 plus 8 a power 4, this is a required question. That terms only we have to send left hand side. And look at here what I had here, minus 5 a power 4 is there, but here what I want, plus 8 a power 4 I want, but here plus 8 a power 4 is not there. A power 6 minus 4 a power 5, which is equivalent to minus 5 a power 4, okay, and minus 3 a power 4, because I want here, why I am doing this, plus 3 a power 4, why I am doing, because if I club these two, will get minus 8 a power 4, here I want 8 a power 4 only, that's why I am adding and subtracting 3. So these two togetherly minus 8 a power 4, so this I will bring to the left hand side, plus 3 a to the power of 4. Okay, next step, this one you bring to the left hand side, so a power 6, so a power 6 minus 4 a power 5. Okay, this I got. Next one, look at the question. After 8 a power 4, what I want? Minus 12 a cube I want. So minus 12 a cube, but here a power 4, but I want a cube term. So for that what I have to do is 3 into this a cube you substitute in terms of a cubes. Look at a power 4 value, look at equation number 3, a power 4 value in terms of cubes you are having, cube and square. So use this third equation, because a power 4 I don't want, here a cube term I want, right? So that's why I'm using this equation number 3. From 3, 4a cube minus 5a square, 4a cube minus 5a square. Okay, since by using equation number 3 from third equation. Okay, now simplify this. So 12a cube, look at 12a cube, that's what I want. 12a cube minus 15a raised to. Okay. What I need to bring to the left hand side is matter. So minus 12a cube I want. So minus 12a cube. So bring this one to LHS side. So a power 6 minus 4 a power 5 plus 8 a power 4 minus 12 a cube. Okay, fine. Up to this I got. And which is minus 15 a square. Okay. What else I want in the left hand side? Look at the question now. Go back to the question. Minus 12 a cube is over. Next 14 a square I want. 14 a square. But here minus 15 a square. So this you write as send. This one you can club as, is it minus 14 or plus 14? Plus 14 a square, right? So this one I can write minus 14 a square minus a square I can write, because total minus 15 a square, and this minus 14 a square you bring to the left hand side. So overall it becomes so a power 6 minus 4 a power 5, okay, plus 8 a power 4 minus 12 times a power 3, and bring this to left hand side. So plus 14 a square over minus a square I got. So therefore this value only we need to compute. So this value only we need to compute. Okay, but this value how much? Minus a square. Or simply if you want you can substitute back what is a square now. So a square is nothing but, use any of the equation. A square means again you have to multiply this, that is not required. Look at equation number this one. Let us call this one star. Roman number 1, that is right. Equation Roman number 1. Look at Roman number 1 equation. A square value 4a minus 5i. So 4a minus 5i. So this is 4a minus 5i, including minus. This is since by using equation Roman number, right? Roman number 1. Equation number 1. So now this will be equals to 5i minus 4 times a. Got it? Now 5 times, what is identity matrix now? 1 0 0 1. Only 2 by 2 matrix you have to take, since a is 2 by 2. Minus 4 into, and matrix A. So you can leave up to this, no problem. 5i minus 4a you can leave, or simply minus a square. For example, if it is a multiple choice question, there will be 4 options. For example, what is the value of this? If it is in terms of a square, you can stop till this, minus a square is the answer. Sometimes it will be linear form. So this is a linear form, 5i minus 4a. Okay, then you may have 5i minus 4a in the option. So accordingly, how to simplify? Keep on simplifying. And what is the given matrix A? So matrix A is 1 2 minus 1 3. 1 2 1 2 minus 1 3. Okay, and this will be 5 minus 4 is 1 0, so minus 8, and 5 0 0, so 4, and 5 1 is 5 minus 12. 5 minus 12 minus 7. Make sure once again. 5 minus 4 1 minus 8 0 plus 4 1 is 4, 5 1 is 5, 5 1 is 5 minus 12 minus 7. So this is the final answer. So this entire value is simply 1 minus 8, 4 minus 7. So you may get doubt. So here also we have done some calculations, right? These kind of calculations. So instead of doing this, simply find out what is a power 6, a power 5, a power 4, a cube, and a square, all these things. If it is 3 by 3 matrix, if it is 4 by 4 matrix, finding a power 6 is a bit difficult task. If it is a more than 3 by 3 matrix. If 3 by 3 also difficult task, how to find a power 6, a power 5, a power 4, and all these powers you have to compute and you have to substitute here, and then you will get the value. But by using Cayley-Hamilton theorem, all those powers are not required. Only the given matrix and identity matrix is enough for this problem itself. Okay, look at given matrix is A. Here look at in these calculations, only A I have used. And identity matrix I used here. A matrix and identity matrix I used. That's it. A square I didn't compute. A cube I didn't compute. Nothing. Only the given matrix only I found the required value. So this is the power of Cayley-Hamilton theorem. And with this I will stop. I will continue in the next class.